Hello everyone, welcome to the module on organic reactions. In this module, we shall look at few kinds of organic reactions and how these reactions are used to transform organic molecules from one functional group to the other. So, this is the content we are going to discuss for this module. That is, we shall begin by looking at an introduction to organic reactions and why one studies them in the first place. Then we shall delve into a bit on substitution reactions and the various kinds, both aliphatic as well as the aromatic versions of it. And then we shall look at addition, elimination, oxidation and reduction reactions. So, the goal of this module is to give you a flavor of organic reactions and how one can do a transformation of one molecule into another. For this module, I would be using mostly the references as the Organic Chemistry 8th edition by Paula Yerkana's Bruce, and also an excellent online resource which is called as Master Organic Chemistry, maintained by Dr. James Ashenhurst. So, for more details I would urge you to go through either of these. So, let us first begin by asking this question of why one should study in organic reactions, right. So, you must be wondering why is this being taught to me. So, to answer this, let us just look around ourselves, and I am sure you will find that many of the things which you use are molecular in nature, such as the electronic devices in your houses or your mobile displays are made up of organic molecules, and these give them the unique features of curved displays or many other features such as excellent brightness. And I am sure you all love chocolates and other kinds of flavors, and many of these let us say the flavors and the fragrances owe their properties to the chemicals or to the organic molecules which are present in them or their active ingredients. And another important area which we are presently using, or which we most of us use at times, are these drugs to keep ourselves healthy, and these again are made up of organic molecules, and these are very critical for keeping oneself healthy. And finally, there is this new upcoming areas in science or in chemistry where molecules are being thought of as small motors which run on a road. Similarly, the individual molecules, which is at the length scale of about 1 to 10 angstroms or 10 to the power minus 10 meters, can act as a motor similar to our cars which run on the streets. They can act as motors and run on any given surface. We can use such properties to come up with functional devices which can do cool things. So, all of this is what we call it as a molecular world, and this molecular world hinges very critically on what is called as organic synthesis. So, by this I mean, if I want to use a given molecule in any of these applications or other kinds of applications, in the first place one should be able to make them in the desired purity and in the desired conformation, configuration and all kinds of things, right. So, that is where organic synthesis plays a very critical and a pivotal role. So, in order to achieve organic synthesis or synthesize a given molecule, which could be a drug molecule or which could be a conjugated polymer for an electronic application, we must first understand how individual molecules and functional groups behave in themselves. That gives us a tool to manipulate different kinds of functional groups and ultimately achieve the transformation we are looking at, and using that we can make the ultimate molecule of interest and use it for various kinds of applications. So, in this sort of a perspective, there has been a significant amount of interest in trying to understand the physical principles which govern the reactivity and the selectivity of organic molecules, and that is where organic chemistry plays a very central role in many kinds of applications which we come across. So, I hope this gives you at least an sort of an overview, an idea of why one studies organic reactions or what is the role of organic reactions in day to day life. And to control all of this, one must be able to understand or to control principles of organic chemistry. And in the next 20 minutes or so, we shall look at some of the aspects of how one goes about controlling the selectivity and reactivity in organic reactions. Alright, having said this, let us begin by looking at what are the basic kinds of organic reactions which are around, and then we shall look into some of them in some detail. So, there are mainly 3 classes of organic reactions or very common ones. The first one is what is called as an addition reaction, and I hope what you can recognize is that we have a cyclohexene. This is being reacted with the HBr, a molecule of HBr, and I hope you see that both the hydrogen and the bromine in the HBr now goes and adds across the double bond, and that is the reason why one calls this an addition reaction. And there are many such reactions in this particular class. And the second class of reaction is what is called as an elimination reaction. Here you have this alkyl halide which has a bromine substituent. If this is reacted with sodium methoxide and in appropriate solvents and temperatures, or reacts with this alkyl halide, and what you end up in is loss of the bromine leading to the formation of the double bond. So, such reactions where halide or other kinds of small leaving groups are lost are called as elimination reactions, and we shall look at some of them in some detail. And finally, another very sort of intuitive to understand class of reactions is what is called as substitution reaction. Here again I have a N-butyl bromide, and this is reacted with sodium cyanide, and the product is the bromo is replaced by the cyano group. So, this is a simple substitution of one group by another group, and these kinds of reactions are what are called as substitution reactions, and there are a number of them. We shall look at them in some detail. I hope you recognize that these classifications are based on simple ways in which the reaction takes place. That is, a reagent is added across an unsaturated double bond like this, or one of the part of a molecule is eliminated, which is why we call it an elimination reaction. And in another substitution reaction, we see that one of the groups is being substituted by another group. So, these are very simple and sort of intuitive to understand, and in addition to this there are other various ways of classifying organic reactions, but this is a simpler way to begin and to understand organic reactions. So, having said this, we shall begin by looking at what are called as substitution reactions, and then later we shall look at both addition as well as the elimination reactions. So, if we talk about substitution reactions, like the one I told you in the previous slide, even among substitution reactions there are various categories or subclasses. So, let us first see what are these subclasses. The first one is what is called as electrophilic aromatic substitution. So, it might look a mouthful, but please bear with me, I will explain this in detail in a minute or so. So, and there is another class of substitution reactions which is called as a nucleophilic aromatic substitution, and finally one can also have a substitution reaction in aliphatic systems, that is systems which are mostly saturated. And among this we can have two kinds of substitution reactions. The first one is called as an SN1 and the second one is called as an SN2 kind of reaction, and both of this classification stem from the mechanism by which this reaction takes place. Okay. So, before we begin talking about substitution reactions, or in more specifically electrophilic aromatic substitutions, I hope you are all aware of what are called as electrophiles and nucleophiles. Electrophiles are species which actually love electrons, that is they are deficient of electrons, or in other words they are typically positively charged systems, and that is where the word electrophile also comes from. Electro stands for the electron, philic stands from loving. So these are the substituents, or these are the kinds of species which love electrons. Similarly, nucleophilic the word nucleophile stands for species which love nucleus, that is they love the positive charge. So these are typically negatively charged species, or which have excess electrons around them. Alright, so now let us begin by looking at what is called as electrophilic aromatic substitution reactions. And in electrophilic aromatic substitutions, there are various kinds of reactions one can find in various textbooks, and some of the common ones are listed here, that is bromination, chlorination, sulfonation, nitration, and Friedel-Crafts alkylation and acylation. So do not get overwhelmed by the number of reactions you see, because they all follow very simple mechanistic paradigm, and that is what we are going to try and understand. So for example, here I have shown you the bromination of benzene with bromine as well as FeBr3, which is a Lewis acid, and this leads to the formation of the bromobenzene. So I hope you see that this CH bond is being now replaced by a CBr bond. So that is the substitution which we are currently interested in, that is a hydrogen on the benzene or any aromatic system is being replaced by, in this case, bromine or any other kind of an electrophile, right. So this is a typical general kind of a reaction where an aromatic system reacts with a electrophilic reagent which is could be generated by itself or in the presence of a Lewis acid as a catalyst, and that would lead to a substitution of one of the hydrogen on the aromatic system by the corresponding electrophile, which could be a bromine, chlorine, or a SO3H or NO2 or any kinds of substituents. Okay. That is how we get this we get these reactions, which is bromination if a hydrogen is replaced by bromine, we call it chlorination if a chlorine group replaces the hydrogen, and we call it sulfonation if an SO3H group replaces, and we call it nitration if the hydrogen is replaced by NO2 by using HNO3 and H2SO4. And similarly with the Friedel-Crafts alkylation, you have an alkyl group, that is a alkane group which replaces the hydrogen, and in the case of the acylation you have an acyl group which is being replaced, that is you have this kind of a group here, you have just R, okay. So these are the substituents which are going to change from a given aromatic system. That is the reason why these are called as correspondingly called as electrophilic aromatic substituents with the following names. So now let us dive into a bit of the mechanism of this and see how does this reaction even take place. So to do this there are 3 steps, and the first one is what is called as generation of an electrophile, and I will illustrate this by using the bromination reaction which I showed you on the previous slide. We have a Br2 here, this reacts with the Lewis acid, that is FeBr3, to give rise to a Br plus and FeBr4 minus, and once this reaction takes place, now you have an electrophile which is this. This is also depicted as E plus, where E stands for the electrophile, and once the electrophile is generated, now this would go and attack the aromatic system. So the next step is the attack of the electrophile. So let us see how does that take place. So I am going to take benzene again, and we have a Br plus, so we are going to go and attack this. So, this would lead to what is called as a carbocation. So, the aromaticity in the aromatic system is currently lost and you have the bromine now attached onto the system. So, this is the second step where the electrophile attacks the nucleophilic benzene, right. And then the next step or the third and the last step would be the restoration of aromaticity or a loss of the H minus to regain the aromaticity. So, that is I am going to redraw the same thing again here. So, now an X minus would come and take away the hydrogen and that would lead to the formation of the product. Okay. So, I hope you see that the reaction involves 3 steps, and the first one is the generation of the electrophile by reaction with the Lewis acid, that is in this case FeBr3, or it could also be AlBr3 or other Lewis acids. In the next step, the generated electrophile attacks the aromatic system of interest, that is in this case the benzene, and that would lead to the carbocation which is shown on the screen, and this carbocation further reacts with an X minus where an hydrogen is lost and the aromaticity is regained. So, the driving force for the last reaction is the restoration of the aromaticity, because the system, if it regains aromaticity, it becomes far more stable, right. So, having understood this, there is a small couple of more minor points which needs to be addressed, that is if I take if I have a substituent here on the benzene, that is I am trying to do this electrophilic aromatic substitution on not on purely benzene, but on a substituted benzene, which could be toluene, which could be aniline, which could be anisole or any other kind of derivative, right. So, in this case the electrophilic aromatic substitution will depend, the position as well as the rate of the reaction will depend on the substituent on the substrate, that is it will depend heavily on what is the X group. So, if the X group is let us say OH, OMe, NH2 and so on and so forth, that is groups which can donate an electron density into the benzene system, they would make it far more facile for the attack of the electrophile, and that would lead to a much faster reaction rate, and in this case the reaction would be more favored at ortho and the para position. So, you will get products which are predominantly ortho and para, right. And if you now take a similar substituents, but which is now an electron withdrawing substituents, let us say I have an X and this X is NO2 or any electron withdrawing groups you can think of, right, strongly electron withdrawing groups. So, these would reduce the electron density on the aromatic system of choice. As a result, attack by the incoming electrophile would be far more slow. So, thus one, the rate of the reaction would be slow, and 2, the products are predominantly favored in what is called as a meta position. So, one can understand why ortho and para positions are favored for electron donating groups and why meta position is favored for electron withdrawing groups by looking at what are called as resonance structures of these benzene substituents. So, I hope one can convince themselves by looking at this, alright. So, having now looked at electrophilic aromatic substitution, both its scope, mechanism and the influence of various substituents, that is either electron donating or electron withdrawing groups on the rate as well as the regioselectivity of the product, we shall now go ahead and look at what is called as nucleophilic aromatic substitution reactions. So here what a typical reaction of a nucleophilic aromatic substitution is shown on the screen, and what you would notice is that you have a bromobenzene derivative with a nitro group at the para position, and if this compound is treated with NaCN, where CN is an electron rich system, so that would act as a nucleophile. So if you would write this again, or let me write this here. So this, the Cn minus is electron rich, so it would act as a nucleophile, and in this case what the reaction taking place is, it goes and attacks onto the carbon which bears the halide, and then this would get substituted to the next one, and as a result you would end up in having the following intermediate. Right. So, this is what one would expect to get the intermediate. So, once this happens, then what typically happens is that this negative charge floats back in, and then you have a loss of Br minus, and that would lead to your product. Right. That would lead to the desired product. So, an important point to note is that the difference between an electrophilic aromatic substitution and a nucleophilic aromatic substitution is that the nucleophilic aromatic substitution takes place on the carbon which bears the halide or the leaving group. So, one can also call this as a leaving group Lg, and what I want you to notice is the following, that this is the carbon which has the bromine, and on the same carbon we have now a cyano group. So, this is the distinction compared to a electrophilic aromatic substitution, where the substitution occurred at ortho and para or meta based on the kind of substituents we had on the initial reactant, right. So, you must be wondering then what is the role of this nitro group, or why is it not emphasizing or explaining the role of the nitro group. So, the role of the nitro group is very critical in this, that is, if you actually look at this intermediate which is formed here, this would be highly resonance stabilized because the NO2 group can pull the electron density towards itself through resonance. As a result, the intermediate gets stabilized enormously, thus the activation energy going from the reactant to the intermediate is substantially lower. Thus, the reaction proceeds forward and leads to the formation of the product. Imagine if you did not have a nitro group. For example, if you had a electron donating group such as an OMe or a NH2 or any other kind of electron donating group, that would significantly destabilize the intermediate which bears a negative charge. Thus, the rate of the reaction would be very slow, and in many cases one may not even obtain the product as well. So, it is very critical to note that typically nucleophilic aromatic substitutions take place more facile, in a more facile manner when they bear electron withdrawing groups, because they tend to stabilize the intermediate. So, this is the intermediate which would be far more stabilized in the presence of electron withdrawing groups such as an NO2 or any other kind of electron withdrawing groups. Okay. I hope this is clear to you all. Alright, so now having looked at electrophilic and nucleophilic aromatic substitutions, now let us go ahead and look at nucleophilic substitution in aliphatic systems. And as I told you previously, there are here two classes, one is called as a SN2 and other is called as an SN1 reaction. So, we will look at each of them in some detail. Here on your screen you see that N-bromobutane or 1-bromobutane is converted into its corresponding cyano product by using sodium cyanide, right. And I have written this as an SN2 reaction. So, the SN2 stands for substitution nucleophilic bimolecular, 2 stands for bimolecular here. So, the S stands for the substitution, N stands for the nucleophilic and 2 stands for bimolecular. So, you must be wondering why is he calling it bimolecular, right. So, actually when these kinds of reactions were discovered or when they were understood roughly 60, 70 years ago, what people were doing they did this reaction, the conversion of the bromide to the cyanide, and then they were interested in looking at what happens if I change or double the concentration of the reactant, either one or both of the reactant. And what they observed is that the rate of the reaction doubles with doubling the concentration of each of the reactant. So, what I mean by that is the following, that is, if I draw rate of this reaction which is shown on the left hand side versus the concentration of the bromide, you do see a linear increase when you go from 1 to 2 to 3 concentration. It could be in millimolar or any units. And similarly, they also observed that if you double the concentration of the sodium cyanide, then one again observed a similar trend, that is a linear trend with the doubling of the rate when the concentration was doubled. So, what this suggested is that maybe the mechanism which is involved in doing this transformation takes place involving both of the molecules, that is both the bromide as well as the cyanide. Okay. And one of the ways to account for this is the following mechanism, that is, I have a carbon which is having a So, I am depicting this carbon now here. Okay. And so, this is what one would encounter as what is called as a transition state, that is, this reactant goes through this pathway to lead to the product which is shown here. And if you look at this, in this both the Cn minus is involved, this will have a delta minus and this will have a delta minus and this will be a delta plus on the carbon. Both the Cn as well as the bromide are involved in the reaction. So, that is the reason why it is called as a bimolecular, because the rate of the reaction depends on both the reactants, and it is a nucleophilic substitution which is very intuitive, because you have a nucleophile Cn minus which is attacking on an alkyl halide, in this case a primary halide, to give rise to the product, right. So, what is important to bear in mind is that this is what is called as a backside attack. You will in chemical jargon, this is called as a backside attack, that is, the incoming nucleophile Cn minus comes from the back of the backside of this carbon which is attached to the bromine and attacks, and the bromide leaves and you form a Cn bond here, C-Cn bond, and the CBr bond gets broken down, right. And a major consequence of this is, in case the carbon which bears the bromide is a stereogenic carbon or it is a chiral carbon center, then an inversion in the stereochemistry is observed. Just to illustrate that, I shall show you an example, that is, let us say I have this molecule and I am going to treat again with sodium cyanide. So, I hope you take note of the fact that the stereochemistry here on this carbon is now opposite compared to reactant and the product, right. So, this is a consequence of the backside attack in the reaction mechanism. And so, this is a very important tool to actually obtain a stereochemistry, desired stereochemistry in a given reaction. And I am sure you are all aware that stereochemistry plays a very important role in the properties of the molecule, and now you are seeing a tool or a technique by which you can play around with the stereochemistry in a substitution reaction. Okay. And the nature of the solvent and the nature of the nucleophile and do dictate to a large extent the outcome of the reaction, and we shall dwell on that in a bit more detail. So, this is what people typically call as an SN2 or a substitution nucleophilic bimolecular, that is because both the molecules, in this case the bromide and the sodium cyanide, are involved in the rate determining step of the reaction, right. And there is another brother or cousin version of this which is called as SN1 reaction, which is again substitution nucleophilic unimolecular reaction. Okay. And here I have shown you an example of this particular reaction where a tertiary butyl bromide reacts with water to give rise to a tertiary butyl alcohol. And here the mechanism is slightly different, and the mechanism is as follows. If you take this, the first step which takes place is the bromide leaves and you would get a planar carbocation plus a Br minus, right. And what people observed is that when they did the similar studies as shown above, they did try to look at the rate of this reaction by varying the concentration of the tertiary butyl bromide, and they observed a linear relationship, whereas when they tried to look at the rate of the reaction as a function of the water concentration, it was actually independent of the concentration of the water. So, what this tells us is that the reaction which we are studying depends only on the concentration of the substrate, which is the tertiary butyl bromide, but it does not depend on the in the nucleophile which is present, which is the water in this case. So, to account for this unimolecular reaction which is depends only on the tertiary butyl bromide, the following reaction is proposed. And the first step is the leaving of the bromide minus, and that generates a carbocation, and this is also the rate determining step of the reaction. And once this happens, then the OH minus H2O attacks, and ultimately one would you will have a loss of proton, and that would lead to the corresponding tertiary butyl alcohol. And this next step is what is typically called as fast, that is fast compared to the previous step, right. And this is another typical example where one can convert a bromide to an alcohol or any other kind of substituted product. And I hope this has given you some sort of an idea or a flavor of what are called as substitution reactions, and we shall stop here now, and in the next lecture we shall look at what are called as elimination reactions, which actually build upon these principles. Thank you.